So we'll continue our discussion related to electrical machines. So far we have been discussing about some basic concepts related to electromagnetic circuits, basically the magnetic effects of electric current, which play an important role in the working principle of almost all the electrical machines. So we have discussed about magnetic field, magnetic flux density, magnetic force, Biotsavart law. So in this video we are going to discuss about another important law which relates the magnetic flux density, the magnetic line of force, the magnetic field lines, and the current flowing through the conductor, and that is called as the Ampere's Circuital Law. So before we discuss Ampere's Circuital Law, we'll just review the Biotsavart Law, which gave us an expression of magnetic flux density at a fixed point away from P. Because it is related to that, that's why I'm switching to it. So just in a quick way, Biotsavart Law basically involves splitting a whole conductor, okay, of length from X to Y into small current elements, each of a small length dl. Combined with the current flowing through it, the product of both is called as IDL, which is called as a small current element. Now each current element contributes to the small portion of magnetic flux density dV vector, and when we sum together everything, the effects of small current elements from X to Y together will get the whole magnetic flux density. So this small magnetic flux density dV vector due to this small current element IDL at a point P at a distance r from this current element is given as this: K IDL sine theta by r square, where theta is the angle between the current element vector, which is tangent to that particular curve, and the position vector r from that point to P, where magnetic flux is to be measured. So the Ampere's Circuital Law, what it does is it gives us a relationship between the current and the magnetic field around it, basically in form of line integral. So the same things are involved: current, magnetic flux density, but here the Ampere's Circuital Law, it says that the line integral of a magnetic field around any closed path in vacuum, air, it is mu 0 times the total current enclosed by that path. Okay, so it can be expressed in mathematical form as this: the closed line integral B vector dot dl vector is equal to mu 0 I. Okay, like this. So let us explain it a bit. Now in order to explain this, let us say we have a long straight conductor, a wire or conductor, whatever. It is carrying a current I. Now the magnetic field lines, it will be in the form of concentric circles around it. So here, in order to prove Ampere's Circuital Law, what we'll do, we'll pick any one concentric circle which is at a fixed distance r from the center O. Now as per the Biotsavart Law, the total magnetic flux density, it will be in mutually perpendicular direction, perpendicular to the plane containing r and dl, which we have explained in Biotsavart Law. dB vector will always be perpendicular to dl and r vector because it is in cross product form, dl vector cross r vector. So dB vector is perpendicular, means the total flux density because of the whole wire will also be perpendicular to that. Okay, so here that value of B vector here, the value of B vector here is mu 0 I by 2 pi r. Now here I could have derived this whole expression using Biotsavart law, using this whole principle k ideal sine theta by r square. I could have done it, but it would have unnecessarily made the whole this video lengthy, because the derivation it would have taken a lot of time, and it can confuse you. So we are discussing just the basic concepts related to electromagnetic circuits. So I did not go into the derivation part. Directly I expressed B is equal to mu 0 I by 2 pi r for a long straight conductor carrying current. So if you want, you can derive it also. If you want, in a separate video maybe I will derive this whole thing, but for now you just understand that the magnetic flux density, the total magnetic flux density due to a long straight wire carrying current I at a distance r from a particular point is given as this mu 0 I by 2 pi r. So we have to prove Ampere's circuital law, that is the line integration of the magnetic field path around the current carrying conductor is given by mu 0 I. So we have taken a magnetic field line of radius r, which is in the form of a concentric circle. We have picked a small portion of length dl. Okay, now here if you see the angle between this dl vector, which will be also in tangent form in the same direction as B vector, they will be parallel to each other. So the angle between them will be 0. The angle between them will be 0. Theta will be 0, because dl vector will also be in the same direction as B vector. B vector and dl vector, they are in the same direction. So theta, the angle between them will be 0. So if we perform B dot dl here, integration of B vector dot dl vector, which is the dot product of the two, it will be B dl cos 0 degree, which is simply B dl. Now B, the magnetic flux density, is mu 0 I by 2 pi r. So it is integration of mu 0 I by 2 pi r into dl. As all of them are constant here, mu 0 I by 2 pi r, it will come outside. So we are particularly integrating this whole concentric circle, the circular path, by dividing it into small lengths dl. So the total integration of dl will be the circumference of this magnetic field path, which is a concentric circle. So it will be 2 pi r, the circumference, the total circumference 2 pi r. So it will be mu 0 I by 2 pi r into 2 pi r, which is equal to mu 0 I. So this proves Ampere's circuital law. Okay, so here the magnetic field line, it encloses this wire carrying current I. The current flows in straight line path through this wire. The magnetic field lines are concentric circles. We picked a certain concentric magnetic field path of radius r. The magnetic flux density, the total magnetic flux density, is in mutually perpendicular direction with respect to it as per Biotsavart law. And we just performed the closed line integral. B vector dot dl vector, the dot product of that. The angle between them is 0 because they are in the same direction, and at every point it will be in the same direction. So it is B dl cos 0 degree, B dl mu 0 I by 2 pi r. As per Biotsavart law, we have not derived it, we have just stated it like this. Maybe I will derive it in a separate videos. For now, it is just that for a straight conductor, the magnetic flux at a distance r away from it, it is given by this mu 0 I by 2 pi r. And we perform the whole integration to get this mu 0 I, which proves Ampere's circuital law. This is the statement of Ampere's circuital law. The closed line integral of a magnetic path enclosing a current flowing through it is given by mu 0 times the total current flowing through the conductor. Okay, so this is Ampere's circuital law, which is very important from the point of view of electrical machines. So I hope you like this video, and please subscribe my channel Engineering Tutorial for more such videos related to engineering, science and technology. Have a great day. Thank you very much.